Today we are going to be talking about free fall. The objectives for today are to be able to solve motion equation problems that involve objects only being acted upon by gravity. So when I talk about free fall, I'm talking about something like if you had a rock or a piece of paper even in your hand and you drop it. You don't throw it, you don't do anything else. The only thing that is acting on it is the force of gravity. Eventually, an object in free fall will reach terminal velocity. Depends on how long it's in the air. Sometimes it doesn't actually get a chance to reach terminal velocity. But what it means to reach terminal velocity is if something that is in free fall reaches a constant velocity and it quits accelerating, that's because air resistance has kept it from accelerating anymore. We won't deal with terminal velocity all the time, but it is a term you need to know. So the acceleration due to gravity, this is related to the force of gravity acting on an object, and we will be talking about the actual force of gravity a little later, but for right now, you just need to know the acceleration due to gravity. And that is named g, called lowercase g, and it is a negative 9.81 meters per second squared. Negative because it's going down, because you're dropping something. The approximate value is 10 meters per second squared. You are allowed to use this on things like tests, on problems. So some of the problems you could do in your head, and you can use 10 meters per second squared just to make life easier. However, you should use 9.81 meters per second squared for labs and when there's a question that asks or refers to it with a precise value. So what does it actually mean to be going 9.81 meters per second squared? Well, if we start off with our rock being dropped off a cliff, at first it is not moving at all, 0 meters per second. Then after 1 second, we're going to add 10 meters per second. So at 1 second, it is going 10 meters per second. And then during the next second, we're going to add another 10 meters per second. So at 2 seconds, it's going 20 meters per second. And then at 3 seconds, it's 30 meters per second. And then at 4 seconds, it's 40 meters per second. And then at 5 seconds, it's 50 meters per second. So as you can see, it is speeding up. Each second, it is speeding up by another 10 meters per second. So it is accelerating by 10 meters per second squared. So I have an example of one of these problems with the equation d equals vit plus 1/2 at squared. So don't forget that these objects are being controlled by gravity. That's the only thing that's being acted on. That's the only thing acting on them is gravity. So again, the acceleration due to gravity, or little g, is negative 9.81 meters per second squared. If you are throwing an object up and then it comes back down, the time it takes to go up, say this was 2 seconds, and the time it takes to go down, it is still 2 seconds. So here's the example. It says a rock is dropped from a cliff and hits the water below in 1.2 seconds. How high is the cliff? Here's our cliff. Here's the rock. Here's the water below. And it's going down. So let's see. We know that the time is 1.2 seconds. As you can see, it doesn't have any kind of acceleration in here, but we can assume that we're on Earth unless it says otherwise. So the acceleration is a negative 9.81 meters per second squared. And we are looking for how high is the cliff. D is, I don't know. Well, that doesn't seem like quite enough information, but what velocity does this rock start off at? It starts off at a velocity, initial velocity, of 0 meters per second. So now we have enough information to go forward. We can use distance equals initial velocity times time plus 1/2 times the acceleration times time squared. And we just plug in. The initial velocity is 0. Anything times 0 is 0, so it does not matter what the time is. This is just going to go to 0. So then we have 1/2 times a negative 9.81 meters per second squared times the time, which is 1.2 seconds, and that's squared. And this is equal to negative 7.0632. And let's check out the units real quick. So we have meters per second squared here. And we have seconds, and those seconds are squared. So that goes away and it becomes meters right here. So it is a negative 7.0632 meters. We're looking for distance. That unit should be meters, so this checks out. So why is this negative right here? Well, this is a displacement right here, not just a distance. And it is saying that is going down. So the negative is in the negative, the distance is in the negative direction. The displacement is in the negative direction. So here is one where we say a ball is being thrown up with a velocity of 12 meters per second. So this time, this velocity, this means an initial velocity. So it is initial velocity is equal to 12 meters per second. How high is a distance or displacement? So that's what we're looking for. Will it get in 2 seconds? So this is going to be a time. So this time the ball is being thrown up. We want to know how high it's going to get in 2 seconds. So the thing that's acting on this ball is gravity. So the acceleration is a negative 9.81 meters per second squared. So then now it really matters to have that negative sign. That's what this problem is for, is to show you the importance of the negative. We're still going to use D equals VIT plus 1/2 AT squared in this problem. We can use other equations. It just doesn't apply in this case because of the variables we have. So if we plug this in, we end up with a distance equals V, which is 12 meters per second, times time is 2 seconds, plus 1/2, and the acceleration is a negative 9.81 meters per second squared, times time of 2 seconds. Okay, so this is 24 meters time, so it's meters per second times a second, so it's meters, plus 1/2 times the negative 9.81 meters per second squared times 2 seconds. This is equal to negative 19.62 and meters per second squared times, oops, this should be a squared right there because it's squared here, times squared. So this is again meters. So 24 meters minus 19.62 meters. This gives us 4.38 meters. So as you can see here, this negative is really important to include. We already checked our units, so we're okay.